in this problem, we're going to find V0 using nodal analysis. We're going to be utilizing the problem-solving strategy on nodal analysis. The first step in that strategy says determine the number of nodes. Okay, so if we look, we have 1, 2, 3, 4, 5. We have one node on the bottom, so we have 5 nodes. We're going to select one as a reference. So let's select the bottom one. So that tells us 4 node voltages. Okay, so now let's assign node voltages. I'm going to assign this one V1. Now remember what the polarity is, plus here, minus at the bottom. V2 plus here, minus all the way at the bottom. We're going to call this node voltage V3 and this one V0. So now I have 4 node voltages, V1, V2, V3, and V0. So that means I'm going to need 4 equations. Okay, now in this problem we have a voltage source connected between a non-reference node and the reference node. So we're going to have a constraint equation. And our constraint equation here is simple. It's V3 equal to 12. Okay, so here's our constraint equation. And then that's one of our 4 equations. Okay. Now, we're going to go in and now apply KCL at the nodes that don't have the voltage source. So that means here, here, and here. So let's start at this node. I'm going to sum currents leaving through resistances and set that equal to the sum of currents entering from sources. So we have V1 over 3K. That's the current here. V1 minus V2 over 6K. Okay, those 2 currents are leaving through resistances. Now if we look at currents entering from sources, we'll have 0.008 entering and then minus 0.002. So collecting terms, we have this equation. Okay, here's our second equation. Now we need 2 more equations. We're going to apply KCL at this node and then KCL at this node. So here's our circuit. Again, we'll show the reference node, V1, V2, V0, and V3. Now we want to work at this node, so we want to apply KCL at that node. Okay, so if we start, we'll have V2 minus V1 over 6K. This is the current leaving in that direction. Current leaving in that direction is V2 minus V3 over 6K. Then we'll have the current leaving this way will be V2 minus V0 over 2K equal to 0. Now if we collect up terms, we'll have minus 1 over 6K times V1. Then we'll have 1 over 6K plus 1 over 6K plus 1 over 2K times V2 minus 1 over 6K times V3 minus 1 over 2K times V0. So there's our third equation. And then last, we'll do KCL here. And if we look, current in that direction, V0 minus V2 over 2K. Current here will be V0 over 1K we'll have a current from this source of 2 milliamps entering. So now we have minus 1 over 2K times V2 plus 1 over 2K plus 1 over 1K times V0 equal to 0.002. Okay, so there's our fourth equation. So now we've got our four equations. There's the first two. Here's the second two. Now, to simplify things a little bit, since one of our equations is very simple, that's just V3 equal to 12, I'm going to go ahead and make the substitution in here. So we only have to solve three equations, three unknowns. In other words, we only have to type in a 3x3 matrix in the MATLAB instead of a 4x4. So if we do that, here's our equation in matrix form to enter in MATLAB. So by making that one substitution, we just reduce the amount of information that we had to plug into MATLAB. We didn't have to. And this term here is tied to that V3 equal to 12, produce that term. So now, using MATLAB, we get V1 is equal to 14.5455. V2 is 7.6364. And V0 is 3.8788, which is our answer.